So thanks for joining us this morning. I realize it's funny when you put together a talk, you look at your slides on a little computer. Sometimes things change when you put them up on the big screen. And I realize when you put the words "up your bus number" on the big screen, it kind of sounds like some kind of Scottish curse. Up your bus number! That's not what we mean. And I'll explain that in a second. But first, I'd like to go through some logistics. So this is a tutorial. This is not a talk. This is not a talk-torial. This is intended to be an interactive session. And to help with that interactivity, Amy and I have brought along a couple of colleagues. So Amy and I, by the way, are research mathematicians, sometimes data scientists. I'm mostly an engineer, from the Tut Institute up in Canada. And we brought along a couple of our colleagues, John and Leland, also from the Tut Institute, to help TA this particular session. And the idea is if you're having trouble, if you're falling behind, if something's not working, we're going to use this old post-it trick. And these fine people are going to come help you. Now, I cannot think of a more overqualified crew of TAs than these fine folks here. So if you do get bored of this particular presentation, if you're well ahead and you have any questions about the fundamentals of data science, especially when it comes to, say, I don't know, clustering or dimension reduction, these are the people to pose those fundamental research questions to. All right, so here's how it's going to work. As we proceed through this tutorial, there will be times when you have some audience participation to be done. I have two colors of Post-its. This color here, orange, is for if you're having trouble. If you're having difficulty with anything at all, just slap this orange Post-it on the back of your laptop, and one of our associates will come and help you out. So if something's not installing, if it's not doing what it should, put one of these on the back of your laptop. Conversely, if everything is going smooth, actually too smoothly, and you're so far ahead that you're getting bored, put one of these on your laptop. That will let us know that we can proceed. We don't have to stall any longer. And we can move along with material. Okay, so green, good. Please proceed. Orange, bad. Please go. We're going to pass these out. Everybody, please take one of each color.
Thank you very much.
Continue.
Yeah. So bus number. What am I talking about when I say bus number? In this particular case, a bus number is the number of people that would have to get hit by a bus before your data science project becomes irreproducible. And for many people, that number is currently 0. That is to say, right now, your data science flow is not reproducible. By the way, how many people in this room right now, the data science work you do, is it fully reproducible? Yes? Hands up? No? Hands down? Not a single hand. Excellent. Good to hear. By the end of this talk, this tutorial, we're hoping we've given you a process by which you can fully reproduce the data science work that you're doing. So we're going to take a couple of minutes now to get started. So if everybody could please pull out your laptop and navigate to this URL, bit.ly/bus_number_help, and follow the instructions there. We're going to take 2 minutes to try and get everything started. Remember the Post-its. If you're having trouble, slap that orange Post-it on the back of your laptop. We'll be back here in 2 minutes to bring you all back on board. Okay, just one quick note. A couple of you have noticed one particular problem already. So has anybody here experienced an error with a package called NBDime? Okay, a couple of you have. Really easy fix. In the bus number directory, how many of you have been able, for those of you who have got that far, you've obviously been able to download to install from the cookie cutter. In that directory that was created, it's called bus number. And the very root of that directory, there's a file called environment.yml. If you're having trouble with this NBDime thing, what I want you to do is I want you to open that environment.yml in a text editor, like say this one. And there's 2 lines you're going to take out. The 2 lines for which there is an error message, NBDime and NBVal. Just take them out, resave that file, and all should be good. Any other questions? Does that make sense? Great.
Other people might get that in a few seconds, Kjell. They're going to need some written.
I'm going to add it to the wiki right now.
Or,
Okay, how many people have been able to get things installed? How many people are still waiting for somebody to come visit them and help them? Okay, I have seen a number of working installations, which is wonderful. I've also seen a few not working installations. But I do want to proceed with the tutorial, so here's what we're going to do. If things are not working for you at all, I highly recommend you turn either to your left or to your right and make a new friend. We're going to pair program. Does that sound reasonable? So for those of you who do have something working, look around, make sure the person next to you looks like they're doing okay. If not, introduce yourself. We're going to work in pairs. And very quickly, we're going to leave this command line and move into the realm of a Jupyter Notebook. And everybody's going to get a lot more happy. OK? Great.
Or do you want to open a notebook right now? They can, because they can follow along the slides.
OK. Ladies and gentlemen, how many of you are here because you want, by the time you leave this room, your data science process to be fully reproducible? Most of you. That's pretty good. For the rest of you, we have to talk. I want to talk to you a bit about reproducible data science. And I want, by the end of this tutorial, two things to happen. One, that everybody leaves this room thinking that reproducible data science is definitely of a benefit to them and they want to do it. And two, we want to leave you with the ability to make your entire data science workflow reproducible. So for those of you who did not raise your hand just now, I want to enter the mind of some of our potential users. My argument is this. Everybody in this room can benefit directly from reproducible data science. Now, I come from an engineering background, which means I do a lot of building of things and testing of things. And so there's this trick that we use when we're building things to try and get them right for our users. It's in UX design, it's the idea of a user persona. So for those of you who don't see themselves in this reproducible data science environment yet, I want to enter the minds of some of our potential users. I want to introduce you to a few characters who may be just like you, may have your types of problems, who are going to benefit from this reproducible data science, this work. Here's a character we're going to visit throughout the rest of this tutorial. His name's Bjorn. Bjorn's a dot-com millionaire. He runs a test kitchen for IKEA. Bjorn's Swedish, but due to his proximity to Finland, he employs a large number of Finnish line clerks. Who knows anything about the Finnish language? Excellent. What do you know about the Finnish language?
It's very difficult for pretty much anybody to learn, let alone people living right next to us.
It's a very difficult language. Why? Because it doesn't resemble any other language really that we know of. Oh, maybe there's Hungarian or Estonian, but that's it. It's a complete dead end linguistically. If you're a Swede, you've got no chance of understanding that Finn next to you unless you happen to speak 5 languages like everybody else in Sweden. Bjorn does not. He wants to build himself a machine learning model to understand Finnish. This is his motivation. But Bjorn's a chef. He doesn't want to have to maintain this model. What do chefs do? They hand things off to their sous chefs to do that job. Bjorn's happy to help build this model in the first place, but when he's done, he wants this to be reproducible so he can give it to somebody else to update later on. Reproducible data science means you don't have to maintain that model forever. You can hand it off to your colleagues. Your colleagues are going to love you. Your employer is going to love you. Your employer is going to have the kind of consistency they need to continue doing their jobs, even if you move on to a better job. Reproducible data science is very good for people like Bjorn. Here's another character you might see yourself in. This is Mark. Mark used to be an astronaut. He had a bit of a bad year, so he decided to leave the astronaut business, move to New York, and start up in fashion. Thing is, Mark's a bit of a science guy. He's got to keep up with tens of thousands of fashion submissions all the time. He wants to use science to do this job. He wants to science the field of data science. He wants to publish a paper about it. But if he's going to publish a paper and he needs to convince his peers, both in the fashion and the data industry, that he knows what he's talking about, his peers have to be able to reproduce his work. He's not from this field. He was an astronaut. To establish his credibility, other people need to be able to do what he's doing. His goal is to publish a paper, get his code accepted into scikit-learn, and change the field of fashion forever. Why does deep reproducible data science help here? Because if your peers can reproduce it, chances are other people are going to use what it is that you're doing. That stuff's going to be valuable not only for you, but the entire data science community. And finally, Annie. Annie writes high-frequency trading software. She doesn't produce products per se, but she's constantly doing EDA. She's constantly looking at her data, trying out new ideas, and then moving on to another one. You never know which one's going to stick, but she really needs to get that edge. Here's the thing, with so many analyses going on all the time, it's very difficult for her to keep track of what she did yesterday, let alone what she did 6 months ago. And when something jumps out of that data, you go, oh wait, I did an analysis, but what did I do? How did I get that result? How did I get that edge? She doesn't want to lose all that work that she's done. She wants to be able to keep track of the data that she's worked with, of what data she put into her models, what those models looked like after she trained them, and what the code that she used to produce those results. All right? Annie's not doing this for a customer. Annie's not doing this for her peers. She's doing it entirely for herself. Reproducible data science means that 6 months down the road, Annie will be able to redo that analysis that she did that one time, that one-off, that EDA for herself. Okay, so let's bring this all together. Who are the potential customers for reproducible data science? Well, it could just be you yourself. It could be 6 months later you, who wants to be able to remember what it was that you did here at PyData. It could be your colleagues. Your colleagues are going to want to be able to take that work from you when you get promoted into that wonderful new job. Or it could be your peers. It could be other people in the data science space. So regardless of whether you're doing data science for yourself, your organization, or the good of the world, there's a very strong case here for reproducibility. So why isn't data science reproducible now? It's got science in the name, right? It should be reproducible. Science is reproducible, right? No laughs? Assuming that science is reproducible, there's a big problem when it comes to doing data science. What is that? Here's a hint. When we're doing data science, how much of our time do we actually spend doing the science part of it? All of it? 10% of it? Closer to that. What do we spend our time doing? Munging data, finding data, cleaning data, dealing with problems in data. We spend our time here. The problem right now with reproducible data science is all of that munging we tend to do off on the side. We tend to do by ourselves, and we tend to just assume once we've got a useful product out of that, that we can just take that, do the science on it, and that science is reproducible, so we're good. The failure here is that munging was not reproducible. 80% of our job is data munging, and it's not reproducible. Now I say 80% because when you're doing supervised learning, it takes a while to train a model. Supervised learning is not the entire space. It gets worse. If you're doing unsupervised learning, quite often you're just doing some kind of EDA and a visualization, how much actual sciencing are you doing? You're running one algorithm out of scikit-learn. 90%, 95% of what you're doing is munging data. So in order to create a truly reproducible data science effort, we need to focus on making every step of this process, whether it be obtaining the data in the first place, ensuring that it's the same data I worked on 6 months ago, processing that data into something useful, and making sure that we are allowed to use that data in the place that we are actually deploying it. That's got to be reproducible. The science part, sure. We have to write good code. We have to document our code. We have to store that code in a source code repository. I would argue we're largely very good at that right now. And we have to deliver that. We have to produce tables. We have to produce images. We have to produce papers. Oh, I haven't talked about that. When you produce a figure for a paper or you produce a figure for a slide, 6 months later, do you know how you produce that figure? Some yeses, many no's. So reproducible data science is about the entire process. So how do we do it? So today, I'm going to take you through one way of doing reproducible data science. This is by no means the only way. We've made some decisions here for you based on the way that we like to work. So some of these I think are great ideas, and you could take these home and run with them if you want. But what I want you to take away is whether you use these exact tools or something similar, you want to accomplish the same thing. So what are some of the right tools for the job of producing reproducible data science? Well, the very first one is revision control. How many people here use Git? Excellent. Git is wonderful for source code. Git is wonderful for maintaining revisions of text documents. How is Git for maintaining data sets? Not so good. Why? Lots of reasons. Data sets are big. Right? They don't store well in a repo. Data sets aren't typically text. They're usually one binary tarball of stuff. Right? What changed between this version and that version? Who knows? The whole binary changed. Okay? So storing data directly in Git is not a great idea. Storing instructions about what to do with data in Git is a good idea. Now, when it comes to revision control, is Git the whole picture? No. Git is a wonderful tool. Like a hammer is a wonderful tool. But a tool is part of something bigger. How many people here use something like GitHub, GitLab, or Bitbucket? What these tools use, these are based around the idea of using Git for something, but what they apply on top of that is a workflow. Git by itself has no notion of a pull request. Anybody who's ever dealt with source code in, say, GitHub knows what a pull request is. Git doesn't. That workflow that you get from environments like GitHub, GitLab, Bitbucket is extremely important, especially when collaborating with your colleagues. You have to share a workflow. So if you use Git today, wonderful. I highly encourage you, if you're not doing so already, to go the next step and use something like GitHub or GitLab to establish a workflow on top of your Git use. So revision control, super important. We're going to use it today. A language. Well, we're at PyData. Anybody here using Python? All right. Anybody here using Julia? Anybody here using something else? R. I know there's at least one in the crowd. Yeah, we go. There we go. All right. Yes, you've got to pick your language of choice. Now, I haven't just said Python here. I said something else. What did I say? Python 3.6. Why did I do that? Why am I being a jerk and why not just, it's hard enough to get people using Python 3. What do you mean this Python 3.6 thing? In my experience so far, incremental changes to Python are great. They add new features which make my job a little bit easier. Starting at Python 3.6, a couple of changes came in that made my job massively easier. What were those changes? One of them is f-strings. Has anybody heard this? F-strings. In Python 3.6, they added a new method of specifying stuff in a string. You want to put text in a string. We used to do it like originally it was just a string and then a %, which is weird, and then a bunch of variable names, inevitably offset from where you wanted to put them in the text. That was terrible. So they came up with a better way. It was dot format. And so now you had a string and dot format and a list of variables that you stuck in there. Anybody who ever tried to fit that on one line of code knows how much of a nightmare that was. Enter f-strings. So f-strings are a huge boon to making your code readable, which to me is a huge boon in making your code reproducible. The other thing that happened in Python 3.6, something called ordered dictionaries. Dictionaries are now ordered by default. When you iterate through the keys of a dictionary, they come back in the order that you put things in. It seems like a really tiny change, but all of a sudden, with that assumption, you can do things a lot easier than you used to do. Now, technically, that was a change made in Python 3.6. It wasn't standardized until Python 3.7, but it doesn't matter, because as of Python 3.6 and onwards, it's there and you can rely on it. So I would argue, if you haven't made the switch already, you should start using Python 3.6 or later to do your data science work. Package managers and virtual environments. We spent a bit of time at the start of this tutorial dealing with package managers. All right. It is tricky at times to get your package manager working. Now, I don't care whether you use Conda or pip in virtual environments or pipenv. That's not true. I do care. But you should definitely use one of these. And the reason is because, as we saw at the beginning of this tutorial, it's difficult to get your environment up and running. Now, we're just doing that for one project, this bus number project. When you start working on another project 6 months down the road, and some of the packages have been updated and things have been changing, if you aren't using a package management environment, if you're not using a virtual environment, if you manage to get that new environment working, the one here from the bus number seminar is going to break. It's just the way of the world. So you want to make sure to use some kind of package manager so that every time you do a project, you can write down, you can record what those dependencies you had and return to that state when it comes time to do this again. Does that make sense? So we've chosen Conda. Why? Because we do data science and Conda makes it really easy. They build lots of stuff for us. They can handle dependencies that aren't just Python. Great. You may choose something else. Pipenv is actually a great choice for this as well. And for reasons, in fact, pipenn does something, and I'll get to a little bit later, that conda does not, and they do it well. Frameworks. Does anybody here use scikit-learn? All right. Everybody here should use scikit-learn. If you program, if you do data science in Python, learn scikit-learn. The one thing they do, let's ignore the fact they implement all these algorithms for us. What they do a really fantastic job of is process. How do I do data science? What does the data science pipeline look like? How do I chain together operations in a reproducible way? Scikit-learn gets a ton of stuff right. Highly recommend you look at it and how they do things. And then buried in scikit-learn is this really cool little tool called joblib. Now joblib has a lot of uses. I actually only use it for one thing, and that is persistence, dumping my data science objects to disk. Right? It's very good at this. Joblib is kind of like a pickle in Python if you've ever used one. Takes an object and writes it out in a format on disk, but it works really well on large data objects like, say, ND arrays, which we tend to use. An IDE, you need a development environment. How many people here use Jupyter Notebooks? How many people here do not use Jupyter Notebooks? Excellent. You guys are going to love this. Start using Jupyter Notebooks. They will transform what you do. Why? Because data science is not about sitting down, designing a project on a whiteboard, and then just implementing it. It's about iteration. It's about interactive processing of your data. And Jupyter Notebooks make that incredibly easy to do. Scripting. Well, scripting. We want to be able to automate what it is we're doing here. Now, the reasons we'll get into a little bit, we use make and makefiles to automate that. Why? Because I'm going to argue that data science is a flow, is a directed acyclic graph of procedures, and make is a tool for doing that. And finally, we started out with a cookie cutter. Why? What's a cookie cutter? There's a way of templating a project. If I want to start a new project today, I don't want to start from scratch. I don't want to try and remember what my development environment looks like. I don't want to try and remember how to set up the config files for all the parts of my flow. What I can do with cookie cutter is I can set up a template that I define once, and then every time I start a new project, it uses that template and customizes it for what I'm doing. Hopefully, most of you got successfully used the cookie cutter this morning to create the environment for this. Right? Highly recommend, if you haven't looked at them before, that you start looking at cookie cutters, and perhaps for your own environment, develop a template for your own use. So these are the tools we're going to use today. As I said at the beginning, you don't have to use these exact tools, but I would argue that you have to use something in each one of these categories if you want your process to be reproducible. All right, this is not a tutorial. I said that at the start. So let's everybody fire up a Jupyter Notebook. So for those of you who are successfully able to create your bus number environment, I want you to change into that environment, source activate bus number, and I want you to fire up a Jupyter Notebook. Type Jupyter Notebook at the command line, and we'll get started. Hands up or green post-its if you've been able to get Jupyter Notebook fired up. For those of you who have not, please buddy up with somebody who has. This is the fun part. So you'll notice when you fire up Jupyter Notebooks, you will likely see a directory list. One of those directories is called Notebooks. Where do you think you should look for our tutorial notebooks? Directory called Notebooks. Excellent choice. And in there, you're going to see something that looks like this. Reproducibility is all about standards. It's all about processes. You can name your Jupyter Notebooks whatever it is that you want. But 6 months down the road, when you're talking to yourself and you're saying, what did I do on that particular project? It's really nice to have conventions about things like notebook names. Where do you think we should start first for this particular data science project? Well, I do have a notebook called Start Here, and that's a good hint, but it also starts with a 10, which just happens to sort to the top of the list. This is a really good idea. In fact, when we're doing reproducible data science, we actually go a little bit further with this. We tend to do the number, which is roughly speaking in which order I should do this. EDA comes first, it's maybe in the 10s, and then sciencing comes second, that's maybe in the 20s or 30s, and then publishing comes third, and that's maybe in the 40s or 50s. And because we typically have multiple developers, we usually put our initials after that. Why? Because I may be working on Notebook 11, and Amy's working on Notebook 11, and we haven't talked yet, but that's okay, because they have different names, and they have initials, so I know who to speak to. And then finally, a little indication of what the notebook is about. It seems like a stupid little detail, but 6 months later, you is going to thank me for making you do something like this. So start with the Start Here notebook, please. So here's the Start Here notebook. This is basically exposition. A lot of this stuff we talked about already. Installing from cookie cutter. If you weren't able to successfully navigate the cookie cutter, I'm going to show you here what it would have looked like. All right? When you fire up a cookie cutter, here's the command right here, you don't actually have to download that code. You can just point it directly at GitHub. And so what we've done here is we've just told cookie cutter to install this thing called Easy Data and check out a branch called PyData New York City. That's it. So that means that I can go and update this cookie cutter on the back end, and you people can get all my updates. Wonderful. Except Kjell, if you update that, you're going to break what it is I worked on. Yes. Another important aspect of reproducibility is if you do something significant, like say give a tutorial at PyData, create yourself a tag. Tag your source code on that particular day, so that when you come back to it 6 months later, you can get back to exactly the same spot in your source code. You may have changed things, and I may change things in this repo tomorrow, but it won't matter to any of you because I'm not going to be working on this PyData New York City branch. Tags are a really important way to do that. So, starting the cookie cutter, you had to specify a project name. That's going to be the name of the directory that was created. We called it bus number. Almost everything else in here you can just hit enter at, and really, really should. This Easy Data cookie cutter started as a fork of something called cookie cutter data science. Cookie cutter data science made a number of decisions. They wanted to support as much stuff out of the box as they could. And so they supported a number of open source licenses and a number of virtual environment managers and a number of versions of Python. I don't want you to use other versions of Python. I really want you to use Python 3.6 or newer. Don't choose to. I don't want you to use virtual env. There's very good reasons to use either conda or even better, pipenv. An open source license, well, you can do whatever you want there. If you want to share your code, please use one of these open source licenses. Don't make up your own license ever. Why? How many lawyers are here in the room? Don't make up your own license ever. That's a job for a lawyer. And people like at MIT or the Berkeley software distribution folks have done very good work to consult with lawyers and make the minimal possible piece of legalese. You should use that. Don't modify it except to put your name in it. And if you want it to be proprietary, go ahead and make it proprietary. That's kind of the default. But at least tell me that. All rights reserved, something in your source code. So we specify the name of the repo. I give my name because it's going to customize a few files for me. A description because it's going to customize a few files for me. And take the defaults for everything else. Lo and behold, it creates this environment. And now for those of you who got it working, you then changed into that environment and used this make command to automate a couple of things. To create your conda environment in the first place, you then activated it. Then you did a second make requirements. Why is that? I'll get to that in a minute. There's some really cool magic there. And then you initialized a Git repository right there. Why? Because you want to know what changes you're making during this tutorial. All the bugs that you're fixing. You want to be able to look back to say what it was like before, what changes did I make. And so you're going to initialize the Git repo. And then you're ready to go. OK, data science process we talked about. What does data science look like? Munge, munge, munge. Oh, then science. And finally, data science is a DAG. What's a DAG? Directed acyclic graph. What are the important features of an acyclic graph, especially when you consider that as a workflow? What does acyclic mean? No cycles. What would it look like if I started a workflow with a cycle in it? It seems like I would never get out of it. All right? Data science is not one of those things. It feels like that at times. But no, at some point it stops. And so data science is a series of steps which eventually stop. And the step that I do now, say I want to work on my data, I want to run it through an algorithm, may have depended on steps before it. But the point is that I may have to indicate, oh yes, before I do this, I have to download and install my data. But that process is eventually going to stop. And there's tools to automate these types of things. And one of the oldest tools for automating processes that were, in fact, an acyclic graph with dependencies is something called make. And we're going to use make files and make in the simplest possible way, and that is to define steps of a process. And all it is for us is a way to associate a bunch of actions to one command. And that one command is going to be make something. Something being the step in the process that we're going to do next. Okay? Now, you don't have to use a make file to do this. I recommend you use something like it, but you don't have to. And in fact, all the things we're going to do from that make file, we can equivalently do in Python for the rest of this tutorial. And we're going to show you how to do that. But here it is. Here is what I'm going to argue is a reproducible data science process start to finish. And what does it look like? The first two steps, make raw and make data. This is the munging step. What's raw? Raw data is when I fetch something from the internet. All right? I get it from someplace, and then I check the versions on it to make sure I know which version it is. Make data. I turn that data now into something that I can use. Is raw data ever usable? If it was, we wouldn't spend 80% of our time munging it, now would we? Raw data is rarely useful, so we have to go through some kind of process of transforming that. So those first two bubbles there represent the munge process. Next, we actually move into science. Maybe we're doing supervised learning, and we're training some kind of model on our data. That'll be the make train step. And once we've got a trained model, we use it to do something. Typically, if we're classifying, say, we're going to make predictions on a data set. Right? That's another step of the process. So that's where the science tends to go. And once we've done that science and produced something out, be it a set of predictions or a transformed data set or whatever it happens to be, then we move into the last step, which is the publishing. Sharing and publishing. I want to analyze that data. I want to take the transformed data, I want to summarize it in some way. That might be creating a table of data that I can put in a paper. That might be creating a visualization that I can put on a slide. That might be just deploying it in a notebook with some kind of interactive bouquet demo. Right? But the point is we're going to reduce our data set to something useful. That's the analysis. And finally, we're going to share it with other people. The purpose of this picture is severalfold. This is a quick reference to the entire reproducible data science flow. It's also a quick reference to where stuff is in this flow, physically on your disk. At the beginning step, it starts on the internet and ends up in directories called data/raw, data/interim, and so on. Next step, you take that stuff from raw and interim and you turn it into processed data saved in some place called data processed, and so on. We're going to walk through this in more detail, but I just wanted you to know this is the quick reference as to what it is we're going to be doing. It's a cheat sheet of sorts, which is why in that bus number repo that you've just now created, I've given you a copy of this cheat sheet. Where is it? It's in a directory called references, in a file called cheat sheet. So should you need this, please feel free to refer to it at any time. By the way, where's the repo? I put it up on a slide at the beginning. Now you've all forgotten. How do I get back to that repo for this particular talk? Anybody know? Here's a hint. Behind me. Corner of every slide, there's a bit.ly link. That will take you to the bus number repo. If at any point you get lost or can't find something, go to this URL. Okay? Everything you need will be there. Let's talk about raw data. Actually, how are we doing? How much time are we at so far? 9:46. Everybody want to put your laptop aside for a second, just like stand up and stretch? An hour and a half is a long time to be sitting here doing data science. Let's stand up, stretch, say hello to your neighbor. 30 seconds. See you back then. Depends. I can answer that.
Yeah, you were super long on that. Super long.
Where's the make file descriptions? Yeah. No, I have it at the bottom of this notebook. No, I don't have it at the bottom of this notebook. It's the bottom of this one. The make files.
Yeah, it's almost, that's like the next step.
Okay.
But are you going to do your raw data as read only, or you want to do your make?
This question was just asked, so I'll do that. Okay, ladies and gentlemen, I'm going to get your attention back. So just as we cut to break there was a question, a very good question, so I wanted to repeat it for everybody. And it just happens to be a question that was answered in that very first notebook. The question was this: what's make doing that a shell script isn't? Okay, why can't I just write a single shell script to do all this for me? And the answer is, make's a little bit more clever than that. Basically, make can just be a series of shell scripts. But what it's doing is it's establishing this graph structure on it, some kind of notion of dependency. So if you're ever wondering what make does, Amy, can you execute that cell? If you're ever wondering what a make command, when I say make raw or anything else, and you're wondering what it's doing under the hood, just do make -n. What that's going to do is just going to display the commands that it would normally run. Okay? So here it's just saying, oh, it would run a Python script that says make environment. Whoops.
My bad.
It would run this Python script and then do this conda command. So if you're ever wondering what make's about to do, you can just type make -n and run it yourself. All right. And by the way, I should mention this. We use a really clever trick that I totally stole from cookie cutter easy data to make our make files self-documenting. So if you just type make, it will tell you all the targets that are available to you based on the comments that are in that make file. This is a really cool trick. You should always use it. So we have a number of targets. A target is just a name that you put after that make command. Amy, can you keep going? Aha. So what does a make file look like under the hood? This thing you see here, thing to build, colon, and a space-separate list of dependencies, this is the magic, and this is the answer to your question. What a makefile is doing is if I tell it to make that thing to build, it's going to know that before I can do that, I have to do everything in that space-separated list. That space-separated list is names of other targets, names of other things in my makefile. So in order to train my model, make train, I have to first build the raw data. I can just put train, colon, data in there, and it will automatically, if it needs to, run that data process first. So it's a really quick way. So you asked about how this is better than a script. Put the script as the thing that you need to run there, but then if there's anything you've got to run before, you can specify it on that target line. And this is just a way of chaining together these various scripts in a way that the flow is automatic. All right, here's an example. Amy, if you could run that one for me. Here's an example makefile. Data, colon, raw. What does that mean? That means data depends on having the process for raw run first. Train test split has no dependencies. Train depends on data and transform data and train test split. Transform data has no dependencies and raw has no dependencies. Okay, wrote that makefile. Amy, can you run that next cell? Okay, if I run this and I say make train, it's going to follow that train of dependencies in whatever order specified there. This is what happens. First it fetches the raw data, then it builds the data sets, then it does a data transformation, then it does a train test split, then it trains the models. I didn't tell it to do things in that order. It figured that out from the makefile. So the really powerful thing here about a makefile is it lets you chain together those little scripts that you write in a sensical way. I used the phrase directed acyclic graph because make hates cycles. Why? Because it would never finish if there was a cycle. So let's write that one out. If I write a makefile that literally links three things together in a circle, what does make do? It's clever enough to notice, wait a minute, I've been here before. I'm never getting out of this loop, and it's just going to abort. So if you make a mistake in your process with a makefile, it'll help you out. If you make a mistake in your process with a script and you write an infinite loop, you'll be there a long time until you realize what you've done. So these are two very good reasons to be using a makefile for this process. So hopefully that answers your question. All right, let's get back to some raw data. The first part of any data science process is acquiring the raw data to do it. And if there's one thing that you take away from this session today, if you want your process to be reproducible, you've got to treat raw data as sacrosanct. You cannot modify it. Why? 6 months later, you will be very angry. How many people in this room, if you did an analysis 6 months ago, how many people in this room could tell me if the upstream data sources changed? What if that CSV file that you depend on was modified upstream? Will you notice that? Don't modify your raw data. What should you do with your raw data instead? Check. Hash it. Check what your raw data looks like. Record the hashes. Record which particular raw data files you used so that you can use that information later. So the whole point of this collect raw data process is simply to go to the internet or wherever you're getting your data from, fetch things, unpack them because they're inevitably in some new compression format that you just found out about yesterday, and check, verify the hashes that you have saved since last time. so that you know if something upstream has changed. And I would argue that if you successfully do analysis, if you do this thing once, you should maybe save a copy of these raw data files somewhere, so that when you come back and realize that Yelp has changed their data set yet again, you still got an older copy of that Yelp data. Right? And you can proceed. Now, where are you going to store that copy? It's not going to be in Git. With raw data files, I highly recommend you go and try out something like use an S3 bucket, use an Amazon, use an Azure bucket, whatever it happens to be. Use some kind of large data storage place to drop these files. And you could do that because all you're doing is dropping raw files, a compressed tarball, a compressed zip file from the internet somewhere on a disk, and you're writing down what the hash of that particular file is. In fact, if you look in that makefile that you've got as part of this bus number project, there's 2 lines in there about talking to S3. Sync to S3 and sync from S3. And what it does is it takes all the stuff, all the raw data that you've downloaded, and shoves it up into a bucket with your S3 credentials. Okay? I didn't do that for this particular tutorial. I didn't use it, but I can recommend you go have a look at that and use something similar in your data process. So this is the data process. Let's take data off the internet. Let's save it in a directory called data raw, and then unpack it to an interim directory. That's the entire raw data process. The next step then is actually doing something with that. So this is where most of your time in the munge process is going to be spent. Starting with that raw data, which you've not touched because it's read-only. Sing it with me. I don't know the tune either, sorry. Is now we're going to process it into something useful. So now we're going to do all the hard part about cleaning, extracting features, and doing a train test split. And more importantly than just doing those processes, we're going to write down the sort of the metadata that goes with it. So for the next part of this tutorial, we're going to do this process. We're going to start munging somebody's data. In this case, I think we're going to start munging Bjorn's data. Yes, we are. So everybody could please fire up notebook number 20. So let's do some data science. If you don't remember, Bjorn, he's the chef. He's Swedish. He doesn't speak a word of Finnish. Everybody in his kitchen does. He thinks they're talking about him. He wants to solve that problem with data science. So he's going to build a model. He searched the internet and found a wonderful project with some Finnish phoneme data on it. He's going to use that to train a classifier. And he's going to try a number of techniques to do that classification and then compare them at the end of the day. OK. So now we can start shift entering through this notebook, which is what Amy's going to do for you. So first, what are we going to do? I just set a data set name. Give it a clever name. Hardest problem in computer science is naming things. So this data set I downloaded from a project called LVQ-Pack, I'm going to name LVQ-Pack. It doesn't matter what I call it. What matters is that I keep using that name throughout this notebook. How do I do that? Computer science gives me something for that. It's a variable. I'll set my data set name to that, and then just refer to that data set name everywhere. So if I change my mind later and think that was a stupid name, I should have called it Bjorn data or something, I can change it in one place. OK, let's keep going. So we're going to save this someplace. I told you my recommendation would be to save it in a path called data/raw, and then unpack stuff to data/interim. Problem. You're probably working on, well, right now you're working on your laptops, so everybody's got lots of space on the laptops, right? Yeah. Sometime during this talk, the warning is going to pop up on mine that says your disk is full. OK, just so you know. If this happens to you, you might know that when you're working with data, often you refer someplace else than where you usually are. If I work on a shared computer at work, for instance, usually the home directories are locked down. So I can't do much in my home directory. Now, I always start my development in my home directory. I forget this. But when it comes time to put the data files somewhere, they've got places where I should put those data files. Other file systems on other computers. So the point is even though I recommend you should use data/raw as a place to store it, you may change your mind. You may want to store it someplace else. Don't hard code paths in your code. What we've done in this particular project is we've imported a source file, source.paths. It's just a very simple Python file, and all it does is it puts those paths in exactly one place. So anytime I want to know where my raw data is stored, I just, from source.paths, import raw data path. And now I can use that everywhere in my code. That means if I change my mind partway through, start moving to someplace that has a lot more disk space or is a lot faster disk, I can change it in that one place and everything will work. I don't have to hunt through every line of code to find my data path. So we do that for just about everything. How many people in here, if you program in Python, use something called pathlib? Oh yeah. You guys should all start using pathlib. Anybody ever type something like this? import os, os.path.append. Here's my old path, here's my new path. Oh, wait, I got to strip off the os.path. What's the strip off thing? Okay, do that first and then add it to this other. Anybody ever done this kind of path name munging? Okay, that sucks. You don't want to do that. And you don't have to do that. There's this wonderful library called pathlib that lets us do crazy stuff like this. Raw data path slash, as in like the divide thing, the rest of my path, and it just magically puts those things together. Okay? Or raw data path dot name or raw data path dot parent or any such like that. It's a really, really useful library, and the really cool part is it works regardless of whether you're using a Windows box, a Mac, a Linux box. It handles all the platform-specific stuff about munging paths. It also looks pretty in your code and is highly readable. And readable means reproducible, right? Yes, readable means reproducible. So everybody start using pathlib. Your code will be prettier. You'll like it a lot more. So from source.utils, we're going to import something called listdir. This is just a silly little function that lists a directory. But because we aren't hard-coding paths anymore, my path is in a variable. So if I want to see what's in it, I don't want to switch to a command line or anything. I'll just run listdir on it. So what's happened? Well, I got some files there. You probably don't have these yet. Let's keep going. Download and check hashes. The first thing we're going to build is something that we've called a raw data set. A raw data set is a collection of files and instructions about how to get them. The best part is that a raw data set can be written out to a text file so you can check it into a source code repo. So we're going to build a raw data set that goes to the internet and fetches the files that we need. In this case, for Bjorn's data set, there's exactly one place we have to go. Here's the URL. So to build a raw data set that knows about this, create a new data set, lvqpack equals raw data set, using that data set name I gave it before, and add a URL to this raw data set. This raw data set's now ready to go to the internet to get it. It hasn't done so yet, but it's ready. Are we done? Is that all I have to do? Not exactly. Now here's something we do very poorly in data science. I can download that data from the internet, but can I use it? Maybe? It's on the internet. I must be able to use it, right? What if I'm shipping a commercial product? Can I use it then? Wait, can I use it in my company at all? These are all really important questions. So I'd argue the first thing you do after you obtain files or find them on the internet is fill in two pieces of information into this raw data set. The first, what is this thing that I've just downloaded? I call that desker, description, right? I should record what it is, where I got it from, and what's in it, just for a human being, not for a computer, for me, 6 months later me, to remind me what this data set's all about. And the second thing we should do is find out if we're allowed to use it. Let's obtain the license for this file. If they're a good data citizen, they've shipped a license with their data. If they're not, you might have to shuffle around and read around on their website to see if you can use it. So we have a few options for adding this information to our raw data set. We always want to keep the data and the instructions on how to use it together for 6 months later you. And so one of the ways we can do that is we can just, if we can find a license file on the internet, we can just add that as another data file. We can just download that license file, we'll tag it as the license, and Bob's your uncle. So we can do that because the README for this particular package that we're downloading is on the internet. That's cool. So what do I want to do? I want to add this extra URL. It's just a text file called README. That's a terrible name, by the way. I don't want to save a text file on my computer called README. Why? Well, because everybody has a file called README. I want to change that to something new, so I'm going to give it a new file name. Datasetname.readme, much clearer. And then I'm going to say this is the description of my raw data set. That name equals. Usually that's just a text string, but if you said name equals desker or name equals license, both uppercase, that's going to tag that as a special piece of metadata. One of those two things. OK, so these were semi-good citizens. They had a README telling me what this file was all about. They didn't have a license file in that on their website. They did have one in the repo, though. So after reading documentation for a while, I came across this thing. I want to put this in my raw data set. I want to store this information about this license, so 6 months later, I can tell if our highly successful phoneme classifier can be used as a commercial product. So here's the license text. Scroll down. I'm just going to specify it as a string. What do I know? Oh, this program is copyrighted in the sense that it may be used for scientific purposes. The package as a whole or parts thereof cannot be included in any commercial applications without written permission. So why did we do this exercise? We did this exercise to verify that we are legitimately using this for scientific purposes. This is reproducible data science. It's right in the title. But we're not using it to ship a commercial product. We can't. And 6 months down the road, when we come back and look at these notes, this raw data set will still be tagged with a license. That's why this is the important second step after you get a file, add the metadata about what it is and whether we're allowed to use it. And now I can just add that metadata from that text string I created up there as a piece of license. And that's it. I've got a raw data file, I've got a license file, and I've got a description text. This is my raw data set. So what am I going to do next? Go get him. Go get a magic box. Fetch that stuff. I don't know what the hashes of any of these files are. It's just something I found on the internet. So I don't tell anything about that. What does this do? This goes and fetches things. Oh, going to grab that off the internet, compute a new hash for it. Grab the other file off the internet, compute a new hash. And it's going to save that information in this raw data set. So that next time I do this, when I load this raw data set up off disk, it's going to check those hashes and tell me whether they've changed or not. OK. So Amy, you can run that cell again. If you do this on your computer, hopefully by now you'll have 3 new files. Anybody able to see that? All right. You successfully fetched raw data from the internet. Excellent. Next step, unpack the data. This is not a very interesting step. Run .unpack on it. So if it happens to, if you download something compressed like a tar file, it will then take that tar file and decompress it to your interim data directory. And that interim data directory is the unpacked version of all the raw files. OK. By the way, can you scroll up just a bit, Amy? When I mentioned pathlib and why it's so cool, it's because I can do stuff like this. OK? Interim data path / dataset name. That's a valid file name. That is so much more readable than os.path.append, this thing with that thing. That's why I love pathlib. OK. So we've got a raw data set object. We've created a raw data set. What is it? Just a collection of files off the internet and some metadata. Now we want to convert this into something that we can use. The name of the object that we're going to basically represent all our data with from now on is a data set. Pretty clever name, huh? Naming things is the most important thing, the hardest problem in computer science. So we're going to build a data set object out of this raw data. What is a data set object? For our purposes, a data set object is data, optionally target information if we're doing supervised learning, and metadata about it. That's it. But by the time we finish the process step, that data attribute of this object is going to be the useful thing for us. So our goal is to transform the raw stuff we downloaded into a data set object in a reproducible way. OK. My raw data set, I can call something called process. And what's it going to do? Nothing. How would it have any clue what data this is right now? It wouldn't. So process isn't going to do anything. But it's going to return a data set object that has metadata because we downloaded a description and a license file. So that's cool. We're halfway there. What do we not have? Oh, I should mention, one of the cute things about the data set object is if you've got metadata, you can just, rather than searching this metadata dictionary for it, you can just use uppercase attributes. So dataset.uppercase license is the metadata field called license. Dataset.uppercase desker is the metadata field called desker, and so forth. There we go. So the last thing we have to do to make this data usable for our purposes is to fill in this data and this target field based on the data itself. All right? Let's do that. So if you look at your interim data directory, you'll find that things have been unpacked to a directory called lvqpack31. What's in there? Source code, because everybody ships their data as part of source code, right? No, why not? That's, in that case, in this particular case, that's what this is. So we look through this directory, we see a bunch of C files, but more importantly, we see, oh, there they are, ex1.dat and ex2.dat. What are these? If we read the README associated with this, it'll tell us. These are our data files. So let's unpack them. Let's create these wonderful pathlib names for them. Make sure they both exist on the disk. Yes, they do. This is good. And take a look at one of them. This is what the data file looks like. What is this? This is process speech data. This is a text file, a space-separated text file that has phoneme data in it. It's actually been processed. It's phonemes that have been recorded and then processed down into a Mel frequency cepstrum coefficient, and the first 20 of these coefficients have been written down here and the label placed at the end. I don't really care about that, but I need to make this usable for my data science purposes. We have to be a bit careful. You can't just use a standard like CSV or something importer for this particular file. Why? Because one of the labels they use is this, which looks suspiciously like that, which is the comment in this file. Right? So we do have to write a custom piece of code to process this. This is not unusual. You download something off the internet, I guarantee 9 times out of 10 you're going to have to write some custom code to process it in some way, shape, or form. So let's do that. We're going to write a function here called read space delimited. It's going to read this file. It's going to convert that space delimited text file into, in our case, a NumPy array. Okay? I'll leave that as an exercise to the reader to figure out what it's doing. But the point is that when I call this function on my data, my test and my training data files, it produces something. It produces a NumPy ND array of this particular shape. Here's my data. It's 1962 lines of 20-dimensional data. And my target vector is also 1962 lines. This is good. I got one target for every piece of data. OK. So I successfully wrote a function to process this raw data and give me something that I can work with as a data scientist. What do I do with it now? I have to attach that to my data set somehow. How do I attach it to my data set? Run that cell for me, please, Amy. Dataset object has is a very simple object. It has in it a name. Datasets always have a name. It has this data thing that we've just computed. It has this target thing if it's a supervised data set, and it has some metadata associated with it. If I want to create a dataset object, all I've got to do is pass these options to it. If I want to write a custom function to process something off the internet and return a dataset object, what I want to do is I want to take whatever logic I've just written and package it up in a function that returns a dictionary. And that dictionary matches this stuff here. That means it's a dictionary with these fields: dataset name, data, target, and metadata. Right? So let's take the function that we just created. Scroll down, please. And we're going to wrap it up. So this is almost exactly what I've done before. I've called this function process LVQPack. I've given it some options called kind is one of the options. That's whether I want the training set or the test set. It's going to do exactly the same stuff that I did before to get that data and the target out. But then when it's done, it's going to create a dictionary. And that dictionary is going to have a data set name, which is the thing I pass into it. It's going to have that data vector that I just created. It's going to have a target vector that I just extracted from that data, and whatever metadata I wanted to store about this. Okay? And it's just going to return that dictionary. Writing a function like this is all you need to do to create a dataset object. So a processing function is something which takes a dataset name and any other options that you want and produces a dictionary. And that dictionary can be used to create a dataset object. So if you scroll down a bit here, Amy. So, Jupyter Notebook trick. If you want to put this function someplace where the code can see it, I recommend you, in this particular case, using a file called localdata.py. Why? Because our code just reads this file and everything's in the namespace. So I want you to save it there. In a Jupyter Notebook, if you put that magical thing at the top, this file, what it's actually going to do is write the contents of this cell to that file. So I'm actually going to write this file to disk, and this is going to become a source file in my repo. I've done that from my notebook, which is kind of fun. So if you do that, if you run that cell, if you uncomment that file thing at the start, run it, you'll see at the bottom, overwriting, blah, blah, blah. I've now created this file. It's now part of my source code repo. And now I can do this from source.data.localdata import process LVQPack, that function here that I just wrote. All right, and what can I do? I can call that function. So it works. I've successfully built a function. I've saved it in a file in my source code repo, and I've used it to build these data sets. That's very cool. So let's add this processing function to this data set, and then we can call it done. So there's two ways to interact with this particular workflow. I mentioned make files. Okay, you can type make raw. You can type make data. You can make train. The other way to interact with these things is through a module or a source file called workflow. I've tried to wrap any function which is going to be useful to this process into this workflow file. Okay, so almost anything you want to do to work with it is going to be workflow.something. So raw data, here's the documentation for it. I wrote you a doc string because I'm a friendly programmer. But the point is that to add this raw data set to our, yeah, that's a lot of doc string. I wrote a lot of doc string. All right, keep going. You can skip that. Move to that. I really like you guys. Okay. So that line at the top, LVQPAC load function equals process LVQPAC. That thing that I imported, that's the magic here. Right? We've already added the raw files. We've already added the license and the description. That's the part that adds the little piece of glue to process this into something useful. And now that I'm done, that LVQPAC raw data set is complete. I want to add it to my personal catalog of raw data sets. Workflow.add raw data set. Okay. And so if I want to use something from my catalog, I can now just say dataset from raw and give it that name. And what's it going to do? It's going to do all this stuff. It's going to go to the internet, fetch those files, check that the hashes that I have are valid, apply the processing function, and at the end of the day, return me a data set with data filled in, target filled in, and all the metadata filled in. This is a fully processed data set at this point. This is an object which you can use to do data science. Okay, scroll a bit more. One of the things that we do in this workflow module is we create sort of a catalog of things for you to use. We give them names. So raw data sets have names. Data sets have names. Transformer functions have names. Scoring functions have names. And whenever we want to join up two pieces of the workflow, we just create a text file of some kind, JSON file usually, that says connect this raw data set to this transformation function. So if I want to turn a raw data set into a full-on data set, I add a very simple transformation function which does nothing. It's kind of the identity function. So add a transformer, starting from a raw data set. Amy, if you could run those, yep. And I get my transformer list, and what have I created? I've created a transformation function that starts with a raw data set named LVQPAC and ends with a data set called LVQPAC. And that's it. So, Amy, could you run this cell here? Make data. Make data is going to do all that. It's going to write, it's going to go to the internet, download the files, or if you've already got them locally, it's going to read those files, check their hashes, make sure they're valid, apply the processing function to it, and write out this data set object on your system. And so when you're done, you can simply do this. Dataset.load with your dataset name. Okay? So I load that up, ask for metadata only, and show me that. And I've got a dataset object. So anytime we want to, 6 months down the road, access this dataset, what have we got? I want to load it up. LVQ, dataset load, database name. In this case, it was called LVQPAC. The object I get back is this dataset object. Okay? In that dataset object, Amy, can I type for a sec? I'll just show you what you got. This is a dataset object. It has metadata associated with it. So LVQ from file dot license. Oops, typing is not my strong point. That's the license information we stored. Desker. That's the description that we stored. Data. This is the thing we're going to use as a data scientist. Target. That's the target array that we're going to use as a data scientist. Basically, everything that we need to be able to do with this data is now packaged up into this, saved on disk so I can load it anytime just by reloading my LVQPAC data set. So what have we done? I'm going to step back a little bit here. We spent most of our time in this tutorial working on the very first part of the process, which is this idea of munging data.
You just need to finish up.
Yeah. When I showed you that workflow diagram at the beginning, make raw, make data, make process, what we've been doing as part of this tutorial is automating those various steps. So if I type workflow.make raw, it's going to do all these steps of fetching the raw stuff from the disk. I'm going to show you where we actually save this, because we're running a little bit short on time now. So the first thing we did was go to the internet and download some files. We saved them in this data raw directory. The next thing we did was we unpacked them. We unpacked them to this directory called lvqpack. Oops. Yep. Then we processed them into this dataset file. This is the thing that we're going to use to do data science from now on. That .dataset. That's the on-disk serialization of this dataset object. If I type dataset.loaddata and I give it that particular name, it will automatically load this object for us. In fact, under the hood, what we were doing is wiring up all the logic to fetch, to do these makefile targets. Fetch raw, unpack raw, process raw, and then make data.
Is that a pickled file?
It is a kind of pickled file. I use a joblib, which does a much better job of pickling NumPy and D arrays. But I guess, you keep pointing at that?
Yeah, I do. Just want to finish off.
I'll finish off. Couple of quick notes. I just want to finish up here with a couple notes about what we've done. Throughout this process, we've been importing stuff from a module called source. This is actually, there's a really cute piece of glue that made all that possible. Source is actually just a directory on our disk. That's where we happen to be keeping all the source files associated with this project. The glue to actually make that work is in this environment YAML file, and it's actually this line right here. When I create environment at the beginning or make requirements at the beginning, what it did was it used pip to install an editable version of the current directory. This line here looked in a setup.py file and said, hey, there's a directory here called source. That's now a Python module. Anything I put in there can be treated like a Python module and, importantly, imported like a Python module. So anything I saved in this particular directory here shows up as importable in my source code. So when I develop a new piece of code, like you saw me do in the notebook here, to process that raw file, if I save that into this particular source path, it just becomes loadable as a module. This is really useful because not only does it mean that you have a place to put your code as you develop it, it means at the end of the day, you've got something that you can ship and share. That is a pip installable module. So all the source code that you've packaged up is already pip installable. You can use it for your notebook. You can share it with your friends. So I'm going to finish up here. Yeah. Flip back to the slides.
Does that include the data sets themselves? Or like packaged up in
It includes the instructions for generating the data sets. So here's what we're going to save. All right. Here's what we're going to save. The instructions that we saved on disk are all saved in the form of JSON files. So I don't have to save these raw data sets because when I make data, I don't load the raw data set from disk. I do if it's there, but if it's not there, I go to the internet, I fetch the raw files, I apply this tiny little function that I wrote to process those into a data set, and I produce that same data set at the end of the day. All right? And every time I do that, I know I get the same source files because I've checked the hash on that. And I get the same outputs out. I get the same data set file out. Does that answer your question? Yeah. So everything that we save is in the form of a text file and easy description. All right. The data science process. So we've processed this data. We've saved this data set out. the next job will be train the models. So we don't have time to go through the rest of this process, but this is the part where we start to get good. And as part of this bus number data science process, we've set up a pipeline of operations that you can do. And I've given you the notebooks that you can now page through and look at this reproducible data science process. So the next thing you would do is typically train these models. You've got a data set, so now you load it up and do data science on it. And you would save those trained models into this directory here. A trained model, for our purposes, is anything that looks like a scikit-learn estimator. That's really important. That's a really powerful thing, because if we use a scikit-learn estimator, it doesn't have to be a single function in scikit-learn. It can be a whole pipeline of them. But the point is, it's the same API to do a pipeline of operations as it is to do a single operation. So we train that model with potentially a whole pipeline of things, and we save it on disk as a pickled version of a trained scikit-learn estimator. That shows up in models trained. And then we transform our data. This was a Finnish phoneme classification task. So the object was to take a look at the input data and produce a prediction vector. All right, and that prediction information will be saved in models output. And we achieve that by flowing our test set through this trained model and saving it on disk in models output. And finally, keep going. There we go. We'd summarize. So the final step we want to do is take those models, analyze them, and produce the summary data necessary. This is actually all automated in these notebooks. So if you flip back, and I'll just finish this up for now. Flip back to these notebooks. You've got this entire process. Starting here, we worked through in gross detail the process of adding and munging a data set. Training and predicting is in this notebook 30, and the analysis part of it is in notebook 40. At the end of this process, the whole the thing is going to end up being scriptable, so that if I change over to, say, a command line, documents, devel, get bus number, I can do source, activate bus number. I can do stuff. Like this. Make raw, fetch my raw data off the internet. Make data, process it. Make train, do the training. Make predict, do the predictions, and so forth. Everything I do is going to be reproducible. Everything I do is going to be savable in a source code repo. And 6 months later, me is going to love me. Sorry, guys, we ran out of time to get into some more meat of the presentation. We got a couple minutes for questions. You can always corner me in the hallway afterwards. And as always, if you want to get hold of us, visit that repo, give us your comments, and thanks for your attention.